In the previous modules, that is module 1 and module 2, we have discussed about different types of ocean structures, coastal structures, their structural form, structural action for different environmental loads, the different types of environmental loads, different wave theories, how to compute these forces, etc. in detail. In module 2, we discussed about the construction methodologies, construction practices, techniques involved in various types of construction of offshore and coastal structures, and also we discussed about the dredging and dredging requirements and various equipments used for dredging. In this module 3, we will discuss about materials which are used for marine environment. For the benefit of the viewers, we will quickly show you the outline of the third module, which we will discuss in the sequence of lectures now. We will talk about materials for marine applications, we will have discuss on different types of materials and their applications to marine environment, properties and selection of materials for marine environment, corrosion and corrosion protection methods for different materials, introduction to composites for marine environment. We will also discuss about various codes of practice for selection of material in marine environment. For the benefit of viewers, let us quickly briefly review what we have discussed in module 1. We discussed about different types of ocean structures. We also discussed in detail various types of structural systems that are deployed for shallow water, medium, deep water and ultra deep waters. We discussed various environmental loads that are acting on offshore structures, how to compute them, what are the different wave theories which are relevant to be used for computing these forces acting on different members of offshore structures. We also discussed about structural action exercised by various types of ocean structures to encounter these applied loads on these members. We also discussed in detail about different types of coastal structures, their structural form, geometric shape, size, dimension and cross section and their applicability in terms of benefits, merits and demerits of coastal structures. In module 2, we discussed about brief outline of planning of ocean structures, brief introduction to design of ocean structures, towing, launching and installation of offshore structures and pipelines. We discussed about regulations and codes of practice. We also had discussions on foundation systems of ocean structures. We also discussed seabed anchors and dredging methods and equipments, different equipments used for dredging at different locations. Ladies and gentlemen, in the third module, we are going to discuss about materials for marine application. This is the first lecture on module number 3. The outline of this lecture will be as follows. We will talk about introduction to material characteristics, because to understand how to select materials for marine application, I must first understand what are those special material characteristics that are important to be looked upon before I select variety of material that can be used for marine applications. Then we will also quickly summarize the suitability of material for marine environment. It means what are those special characteristics, physical, structural, to be looked upon so that I can select the material based on these requirements. The different materials have chances of getting applied for marine application. There can be ferrous and non-ferrous metals. You can have non-metals like fiberglass, glass, concrete and wood, which find application in marine environment. You can also have composites, which are fastly being used in marine application. Of course, concrete can never be ignored as one of the primary material for construction of ocean structures. If you look at the flow diagram which is being given here, if you look at material as a core area of my interest, I have got metals. Metals can be ferrous and non-ferrous, which can be, for example, mild steel, for example, copper, aluminum and brass. I can also have plastics, which can be thermosetting and thermoplastic resins, which can be acrylic, polythene and polyvinyl chloride, which we call PVC, which also has application in marine environment. If you look at the environmental issues related to selection of material, then recycling, sustainability, renewable, toxic and non-toxic are some important domains of interest which people focus on environmental issues related to materials being used in environmental practices. If you look at different kinds of other material than metals, say for example wood, there can be natural and man made varieties of wood. Natural wood can be pine, mahogany and oak, whereas man made can be plywood, chipboard, MDF, etc. Sometimes people use geomembranes and textiles also as material for marine application, cotton, wool, silk, dyes, natural, etc., because they can be also used as type of protection and chemical coatings which has been used. People also use chemicals for finishes of members on marine environment. So, marine environment has a very complex level of application and wide variety of material have been used in practice in the marine environment. So, our interest is to look at those fundamental characteristics which are very important for selecting material for marine environment. What are the mechanical properties of metals which are very important, which will guide us to select material for ocean environment? The mechanical properties are generally considered as an important index to study the behavior of metals under loads. For example, strength, hardness, toughness, elasticity, plasticity, brittleness, ductility, malleability are some of the very important properties of mechanical index properties which can be useful to understand the behavior of metals under given loads. Now, these properties are described in terms of types of forces or stresses that the metal must withstand and how these forces are resisted. So, depending upon the pattern they resist, the methodology they resist, and of course, depending upon the type of action of these forces on this material, then these properties are redefined slightly and intrinsically. Let us then understand what are the different types of forces or stresses that act on members in offshore structures. There are common types of stresses which can be classified as follows. I can have a compressive stress or a compressive force acting on the member. I can have a tensile force or tensile stress generated on members. We can have shear force coming on the members. We can also have torsional effect on members and impact forces which can be caused by the vessels or tugboats on the members during impact. And interestingly, a combination of these stresses is the most critical way we must look at them. So, if they act independently or they act in the absence of others, then the problems are lesser, but if they combine together, then I may encounter in different kinds of problems. Like one example is a fatigue problem, which is reversal of forces in terms of, let us say, tension and axial compression. There is a very interesting figure which is a stress strain curve which all of us as engineering students know. Let us quickly understand what is the importance of this in selection of material for marine environment. It is a classical stress strain curve for a ductile material which I am showing here. There are different points which I am indicating here, 1, 2, 3 and 4, whereas 1 stands for the ultimate strength of the member, which is an index shown in the stress axis. Yield strength is the point from which the yield level can be estimated, which is again a strength value shown on the stress axis. Of course, the limit of proportionality or proportional limit stress is up to which the stress strain curve remains linear, which we all understand, and 4 can be the point of rupture where the material actually forms neck and ruptures. In case when you are not able to define the yield point very clearly, because most ductile material other than steel do not pronouncedly show a well defined yield point. In such cases, what we do is we plot a 0.2% typical strain offset and draw a parallel line which is parallel to the initial slope of this line. Wherever this line is intersecting my so called stress strain curve, I obtain that as my yield point. This method is what we call as offset yield method. In case of brittle material, this story is slightly different. Brittle materials such as concrete or ceramics do not have a designated yield point. In such cases, rupture strength and the ultimate strength are exactly the same for these members. The area underneath this stress strain curve is an index of toughness of the material. So, toughness is on the other hand energy of the material which can absorb prior to rupturing of the material. Now let us quickly look at the effects of marine environment on members or materials used for ocean structures. Earlier the major application of material is only with the surface ships. Now the ocean systems require material with special characteristics. Offshore drilling and production platforms, surface buoys, instrumentation platforms, submarine vehicles are new kinds of ocean systems which demand special characteristics of material which can be used or applied on them. Now interestingly, let us quickly look at what are the exposures which are meant for ocean structures. Ocean structures are exposed to different environmental weather as wind, waves, ocean currents coupled with thermal gradient and ice. Of course, environmental effects which can be caused by these on material are the following. It can have a chemical effect on the material, it can have a fatigue failure on the material, and of course the stress and corrosion effects are also equally important, which are after effects of these environmental effects on the materials. Interestingly, in the recent time, because of the environmental impact assessment becoming very important for offshore structures or coastal structures, biofouling effects are also considered to be an important parameter to estimate the deterioration characteristics of the material and the effect of this material after deterioration on the environment. So biofouling effects also form a very important effect which is caused by on the material by these environmental forces. Now let us ask a fundamental question. Under the given complex system of different kinds of forces acting on the member, different combination of forces acting on the members of offshore structures or ocean structures, what characteristics do the material should possess? Because I must understand what do the material actually need to qualify to be used for ocean structures and systems. Materials must have properties which ensures fundamentally survivability under this environment. The moment I say survivability, then it should survive in case of collision, it should survive in case of excessive loading which can occur during hurricanes or special kinds of environmental forces, it should withstand a severe hydrostatic pressure. Ladies and gentlemen, interestingly can only name very few situations where these kinds of conditions are imposed on material to withstand which are highly uncertain. For example, land based structures may not have to undergo the forces which are relating from accidents very often, whereas in ocean structures or offshore structures collision is considered to be one of the day to day life load which happens because tugboats keep on offloading the fuel from the platform or the crude oil from the production systems will always have a tendency, or there is a high probability that these vessels may touch or may rub upon the members of structural systems. So in case of accidents, in case of excessive loads which are caused by uncertainties during hurricanes, and in case of excessive hydrostatic pressure, materials must remain intact, which we call they should have very high degree of survivability. In addition, structures are also exposed to earthquakes, hurricanes, scouring effects and typhoons, etc. Now look at an offshore structural system under the present environmental loading. There is a very good combination, or rather there is a very serious combination of different kinds of force systems, different combination of these forces acting on the members, different effects caused by the environmental nature on the member material, and material also have specific physical and structural characteristics. Now the algorithm of selection of material for offshore structural system is growing complex in nature, and therefore we must clearly understand a guideline how to select this material for ocean applications. Therefore materials are subject to different kinds or different types of loads and their combinations, which is very critical for us to understand before we go for selection of material. Therefore it requires specific properties to sustain these loads. What are those specific properties which are demanded from the material if they have got to qualify for ocean structures or ocean systems? Now, selection of material is a very important phenomena which we must understand thoroughly before we study important characteristic material that is to be used in offshore structural systems. We must understand, ladies and gentlemen, there exists a very close relationship between the selection of material and the type of structure. Various specifications, codes, regulatory agencies guide the application of material in marine environment. There is no doubt about it. You have got different varieties of codes which will govern some suggestions which will recommend certain ideas and certain methodologies based on which you can select the material for marine environment. For example, American Bureau of Shipping recommend guidelines of use of material for surface ships. Different codes and regulations are also desirable. Instead of following a unique or a single code, we must go for different codes and regulations available. It is not a requirement following different kinds of codes, because since it may limit the selection of material. If you go for only one specific code, then the material recommended by this code becomes mandatory for us to use in the marine environment. So, it is not always mandatory you must follow only one exclusive code, but of course different varieties of codes suggest different methodologies by which can select the material for marine environment. Following factors should also be considered while selecting material for marine environment. Let us see what are they. You must understand thoroughly the physical and chemical properties of the materials. We must also look into the cost factor, because offshore structures are capex cost of very high index. The fabrication facilities is a one important governing guideline if you want to select a material for offshore structural fabrication systems, because the material should be constructible and fabricatable, because it is very important for us to make it easy and comfortable for the manufacturer or for the contractor to fabricate the system which is designed in the shop floor. And interestingly, expected maintenance must be there for putting the survivability of these kind of structural systems under the complex ocean environment. So, selection of material is closely governed by advice or recommendations given by various international codes. This gives us variety to select material depending upon different guidelines and recommendations. Secondly, various factors we must focus to select a material for marine application. Physical and chemical properties of the material, the cost factor, the fabrication facilities and expected maintenance are important guidelines for us to understand how to select a material for ocean systems. Following factors should also be considered. Material should be chosen such that the catastrophic failure should be avoided. It means the failure, if at all occurs, even at a lower probability, should not be sudden or immediate, because a lot amount of qualitative and quantitative assets are invested on offshore platforms. So, the platform or the material or the design or the geometry should give me an interesting warning before it starts ending up in a catastrophic failure. So, materials should be chosen carefully so that catastrophic failure should not occur. Materials must also withstand hazards. What do you understand by hazards? Where do they arise from? They can be hazards which can arise from operational errors. Ladies and gentlemen, remember, offshore process or oil production process is a complex system. It involves lot of electromechanical and electrical and instrumentation equipments which has got to be synchronized in a specific format to actually successfully do a drilling or a production of crude oil or any fossil fuel from the seabed. So, because of its integration of different kinds of equipment systems, we must always see that the material selected should be capable of withstanding the foreseen hazards, besides these meeting the design requirements. Let us look at different kinds of sea states for which the offshore structural system will be subjected to. Sea states refer to height, period, character of waves on the surface of large body of water. Essentially, they are simple scales which are used to give a rough description of the current conditions, primarily for reporting in a ship's log or similar. Let us quickly look at very briefly the design considerations based on which material must be selected. In selecting a material for marine application, the following physical characteristics of the material are very important. Foremost is of course the yield strength of the material, because based on the yield strength it gives me a guideline how to design the member. The second characteristic which is very important, and of course please do not understand that they are all in the same ascending order. I am not putting them in a specific order, I am only listing them. Young's modulus is also an important characteristic which will govern the deflection and bending of the structural members. Poisson's ratio is also important because we are dealing with multi-axis loading analysis in offshore structural members. Fatigue performance is very important because reversal of forces is an inherent characteristic of environmental load which encounters this kind of ocean structural systems. And of course fracture resistance is a very important phenomena which is demanded from the material in offshore structural systems. So in the design point of view, yield strength, Young's modulus, Poisson's ratio are very important. Sometimes in design considerations fatigue and fracture resistance are also equally necessary to be focused before we select a material for marine environment. So I put all of them as physical characteristics for selection of material. In addition, physical characteristics present in the literature are very important to understand that they are only indicative. For example, if the material has a yield value of let us say 250 megapascal, it is only an indicative value which is for a standard specimen, but in reality depending upon the material what you are trying to use, the structural loading in the actual environment may vary these kind of properties in reality. So there is a marked difference which exists between the data which you have based on the laboratory tests and in situ conditions, because the material or the member will be subjected to different combination of forces which can alter the properties which has been studied in the strict laboratory conditions. Therefore, this warrants a change in allowable stress levels for various ocean conditions. It means in short the physical characteristics of a given material which are indicative, which are available from the laboratory experiments are only guidelines. You cannot use them directly, you have got to, or you need to alter them or appropriately modify them to suit different stress levels which are actually encountering the members in ocean systems or ocean environment. So how this is taken care of in the design? This can be taken care of in terms of what we call material allowance. You can also increase the thickness of the member than that is actually marginally required based on design consideration, because that allowance in increase in thickness can take care of uncertainties which is caused by change in the conditions in the ocean environment. You can also use what we call appropriate factor of safety. So these are some of the methods by which one accounts for the variation in the stress values of the material under marine environment. Let us now look at one specific material in this lecture and try to classify this as applicable to selection of this material for ocean structural systems. Let us say for example steel is a fundamental material which is very popularly and widely and largely being used for ocean structures. So steel are classified by a variety what I am going to list now here. Steel is classified based on composition, maybe it is called as carbon, low alloy or stainless steel. You can also classify steel based on manufacturing methods as electric furnace or open hearth basic oxygen. You can also classify steel based on the finishing methods, it can be either called as hot rolling or cold rolling. You can also classify steel based on its microstructure as ferritic, pyrolytic or martensitic. It is also classified based on the required strength level which is specified in different standards. Ladies and gentlemen, please understand that the strength requirement of material, for example steel, is also variedly different in different international codes and regulations. It is not uniform everywhere, depending upon where you are going to apply this material, on which component of the member you are going to apply, the yield strength or the strength recommendations given by the codes vary. So, we must really understand the steel can also be classified based on these strength level requirements. Based on heat treatment, can also classify steel as annealing, quenching and tempering. Now, based on the product form, the final geometric form, of course we understand as structural engineers, steel can also be classified as bars, plates, sheets, strips, tubes or of any other structural shape which has been given a name depending upon its manufacturing cross sectional dimensions. So, steel classification has got a wide variety. So, it is very important for us to understand how are we going to classify steel for my application in motion structural system. Am I going to classify based on its composition? Am I going to look at the strength requirements of this material? Am I going to look at the finishing methodologies based on which I am going to classify? Am I going to look at the product form? So, ladies and gentlemen, please do not recognize classification of steel as simply cross sectional shapes like bars, members, plates, etc. Steel classification, especially as applied to offshore structural system, is having a very wide variety and they also differ in different kinds of international codes. Now, if you look at steel classification based on carbon alone, you can further classify this as low carbon steel, medium carbon steel and high carbon steel. So, low carbon steel is the one which has got less than or equal to 0.3% carbon. It does not contain other elements like chromium, cobalt and nickel, whereas medium carbon steel has a percentage of carbon varying from 0.3 to 0.6% and high carbon steel has content varying from 0.6 to 1% of carbon. So, carbon plays a very important role in altering the physical and structural characteristics of steel. You also have ultra high carbon steel which is having percentage as high as 2 in its chemical composition. Can also classify steel further based on its strength, as I said, low strength steel, medium strength and high strength steel. Now, let us quickly look at what we understand by a low strength steel. It is also called as low carbon steel. Yield strength is lesser than 415 megapascal. The merchant vessels must meet this requirement, of course of different respective country codes besides any other regulatory body. This is a widely used material essentially for hull structures, fittings, tank instrument fittings and buoys. Low strength steel has got specific application in ocean structural systems. It can be used for manufacturing or fabricating hull systems, can be used for fittings and appurtenances, can be used for tanks, can be used for manufacturing buoys. Ladies and gentlemen, it is very interesting. It is the first time probably you may be hearing that steel is classified depending upon, or a material is classified depending upon where you are going to use this material specifically. So, ladies and gentlemen, international codes applied in offshore structural system are very intrinsic and very clear. They categorically design and say what kind of material should be used at what location of the member. For example, you can see here very clearly the hull structural systems, fittings and appurtenances and tanks and buoys can have low strength steel as a preferable material. For example, ASTM A242, A441 are widely used for pressure vessels. If you look at the medium strength steel, the yield strength varies from 1035 megapascal, it varies from 415 and it goes till 1035 megapascal. It is widely used as material for ice breakers and buoys in Arctic regions. Remember, again I am insisting that material are classified. For example, steel in this specific example is classified in international codes not only dependent upon strength, but also they are recommending their applicability for different kinds of members used in different regions as well as Arctic region, etc. So, it is very interesting and very detailed. Therefore, these detailed guidelines which are available in international codes helps us to select material very comfortably and very easily. If you look at high strength steel, yield strength is greater than 1035 megapascal, is one of the very high value, probably in design of onshore structural systems like buildings, etc. You must have never encountered a steel whose yield strength is higher than 1000 megapascal. In reinforced concrete structural systems, we have been using steel, it is about 550 megapascal or maybe 415. whereas we have an yield strength here which is as high as 1035 megapascal. We also have a special kind of steel which is called maraging steel, which has yield strength varying from 1 gigapascal to 2 gigapascal approximately. It is a very surprising and very categorically recommended steel which is having a relatively very highly ductile and heat treated to improve these kind of properties. This is what we call as maraging steel. Now let us quickly look at what are the different kinds of codes and what are the recommendations given by the codes. I am not giving the name of the codes, they are available in the reference already given to you in the web page of NPTEL IIT Madras for this course. I am not looking at the names of these codes, I am now going to suggest how these codes guide me to select material for offshore structural systems. Structural steel plates for offshore structures differ because of the varying fields of application and location where they are being used. 4 major standards are existing besides shipbuilding standards. Let us quickly see what are they. These standards are PREN 10225, BS 7191 and the material data sheets based on Norwegian standards and primarily which are applicable in North Sea in Europe. The APS standard is mainly applied in American and Asian regions. However, there is no bar that these standards cannot be used in other areas. In some parts the standards corresponds to each other, in some class, in some specific codal applications these standards also match the values exactly with each other. So the NORSOC standard refers to PREN 10225 which itself is having a basis of derivation from BS 7191. Therefore codes can also be used for different regions. Now how codes actually classify steel for offshore applications? Remember, I am now looking at classification of steel from the codes for offshore applications, where I am going to apply the applicability or the member location within a specific structural system. So if you look at steel groups based on APRP2A working stress design code, how APRP2A groups the steel? Steel is grouped according to the strength level and welding characteristics. Very interestingly, not only based on strength but also weldability is also seen as one of the important element to group steel for structural application as per American Petroleum Institute recommended practice 2A working stress design. It groups a group 1, group 2 and group 3. Group 1 are steels with specific minimum yield strength, what I call SMYS, specific minimum yield strength of 280 megapascal or lesser and carbon equivalency 0.4% or lesser, because carbon equivalency will guide the weldable characteristics of any steel. If you look at group 2, it varies from 280 to 360. The carbon equivalency is up to 0.45 or higher. It requires the use of low hydrogen welding process. Even the welding process is also guided specifically by this code. If you look at group 3, the high strength steel which is having yield value more than 360 megapascal, special welding procedures for the steel are recommended by the code. Investigation of failure related problems are mandatory if you use the steel for design. If you look at steel again further, steel structures for design in offshore structural system, strength is not the only criteria, remember that. Should have a good superior low temperature toughness for the base metal and the welded joints, because this kind of combination with better strength and low temperature toughness will improve its weldability as well as it will avoid brittle failure. In addition to Charpy's impact test properties which are mandatory for steel to be selected on strength basis, material also requires good CTOD. CTOD stands for crack, tip, opening, displacement characteristics. They are also important for selecting. CTOD is one of the important family of fracture mechanics tests that measures the resistance of material to growing of a crack. Look at steel toughness. Toughness is used to two quite separate quantities. One is what we call impact toughness, other is fracture toughness. Impact toughness is an energy measured in joules and commonly related to Charpy's V0 test, whereas fracture toughness is calculated value for a critical stress intensity factor. Crack tip opening displacement test or J integral test will qualify these kind of values. So toughness may be loosely described as a measure of resistance to failure in the presence of crack, notch or a similar stress concentrator. So, we must understand that it is one of the important requirement for selecting a material for offshore structural systems, because we always have a probability of stress concentration occurring at the joints of the members in a given structural system in offshore structural systems. High toughness therefore is generally recognized as a desirable characteristic of offshore steel. High toughness material is one where considerable amount of plastic deformation is required at the crack dip before the crack can be made to advanced. Conversely, if the application of stress causes elastic failure of atomic bonds at the crack tip, relatively little energy of deformation is involved and the results in a brittle failure. So, it is very important to understand the CTOD characteristics also as one of the consideration for selecting material which is recommended by APRP. Steel classifications based on APRP 2A WSD further says steel can be grouped based on the notch toughness characteristics from impactors class C, class B and class A. Class C, no impactors are specified. Primarily structural members involving limited thickness and moderate forming can use class C. It is low restraint, modest test concentration and quasi static loading are the specific probable areas where this kind of steel can be recommended for offshore application. Examples can be piling, jacket braces, jacket legs, deck beams and legs of offshore platforms. When you have got sub-freezing temperature requirements, then you must look for class A steel which is recommended for this kind of regional applications. Offshore structural steel can also be recommended based, for example, fixed offshore structures. You can use medium gauge structural steel with yield strength typically in the range of 350 megapascal. These steel structures or these steel are well documented and covered by existing standards and codes very well. In recent years, there has been increasing interest of using high strength steel for these installations. The benefits are increase in strength to weight ratio and saving in cost of material. As a result, significant parts of several platforms, for example jackets and topsides, have been constructed using 400 to 450 megapascal steel of yield strength which are installed in North Sea. However, to date fatigue sensitive components, for example tubular joints, have generally been fabricated from medium strength steel because of the better knowledge on these steel regarding fatigue performance and lack of increased performance of high strength steel in this area. The principal application of variant steel has been in fabrication of jack-up bricks. Steel with nominal yield strength ranging from 500 to 800 megapascal have been used for fabrication of legs, racks and pinions and spud cans of jack-up bricks. If you look down further, high strength steel are used in tethering attachments for floating structures in TLPs, also used for mooring lines with semi-submerged in case of mobile offshore drilling units. High strength steel defined as yield strength more than 350 megapascal are commonly used. About 40% of offshore structural systems use this as per a survey shown in 1994. So, it is a very interesting table which gives me the strength of steel, the process routing and the application areas. For example, 350X52 is a normalized TMCP steel which is used for structures and pipelines. TMCP stands for thermomechanically controlled processing, Q stands for quenching and T stands for tempering. So, different strength of steel as per the grades is depending upon the process routes and depending upon the application area are shown in a summary here for the benefit of the readers. Thank you very much.